Gravity shapes the cosmos. It dictates the dance of planets and the birth of stars. Yet it remains the most enigmatic of forces. Its quantum nature eludes our grasp. We seek new ways to explore its mysteries. Could we simulate aspects of gravity in a lab? This is not about creating a planet, it is about mimicking gravitational effects. We explore a fascinating idea today. Can spinning electromagnetic fields and electrons achieve this? Can they create a form of artificial gravity? This journey delves into that very possibility, a quest for understanding. The universe presents grand gravitational laboratories. Black holes and neutron stars offer extreme conditions. However, these are light years away. Observing them directly is incredibly challenging. We desire more accessible experimental setups. What if we could create analogs? These would be systems that behave like gravitational phenomena. They would not be gravity itself. Instead, they would share similar mathematical descriptions. Such analogs could offer profound insights. They might illuminate the deep connections between different physical laws, a truly exciting prospect for modern physics. Our focus turns to electrons. These tiny particles are fundamental. They carry electric charge and have mass. We usually think of their electromagnetic interactions, but their mass, however small, means they also interact gravitationally. Could dense collections of electrons manipulated by powerful fields reveal something new? Every object with mass exerts a gravitational pull. This is a cornerstone of Einstein's general relativity. Electrons, though incredibly light, are no exception. A single electron's gravity is minuscule. It is virtually undetectable in everyday circumstances. However, when electrons are packed together in vast numbers, their collective mass becomes significant. This collective mass can indeed become a substantial source of gravity. We see this principle at play in the cosmos. The universe itself provides compelling examples of this. Consider white dwarf stars. These are the dense remnants of stars like our sun. After exhausting their nuclear fuel, they collapse. Their matter is squeezed into an incredibly small volume. A white dwarf can have the mass of the sun, yet it might only be the size of Earth. Electrons play a crucial role in supporting these stars. They form a degenerate gas. This electron degeneracy pressure counteracts further gravitational collapse. The sheer density of electrons contributes significantly to the white dwarf's overall gravitational field, a testament to their collective power. The concept of electron mass contributing to gravity is not new. It is an accepted part of astrophysics. Electromagnetic fields are powerful tools. They can guide and confine charged particles. Electrons with their negative charge are particularly responsive. Scientists have developed sophisticated devices to exploit this. Tokamaks are one such example. These machines use strong magnetic fields. The fields are shaped like a torus, a donut. They confine superheated plasma, a gas of ions and electrons. The electrons within a tokamak spiral along magnetic field lines. They can reach very high speeds, approaching the speed of light. Another fascinating device is the penning trap. Penning traps use a combination of electric and magnetic fields. The static electric field confines particles axially. The strong, uniform magnetic field confines them radially. This creates a tiny prison for charged particles. Individual electrons or ions can be held for long periods. They can be cooled to extremely low temperatures. Or, they can be manipulated with precision. In these traps, electrons also follow complex spiraling paths. Their motion is precisely controlled by the applied fields. When electrons are accelerated to near light speed, relativistic effects become important. Their apparent mass increases. Time, from their perspective, slows down relative to a stationary observer. These are predictions of Einstein's special relativity. They have been confirmed countless times in experiments. Imagine a dense shell of electrons. These electrons are not static, they are spiraling at incredibly high speeds. This motion is driven by powerful rotating electromagnetic fields. The fields act like a dynamic container. They hold the electrons in this specific configuration. This rapidly moving shell of charge and mass creates its own complex electromagnetic environment. It is this environment, and the behavior of energy within and around it, that interests us. Could it act like a boundary for certain types of energy or particles? The high-speed motion of these electrons is critical. As they spiral, they generate their own electromagnetic fields. These fields interact with the applied fields. They also interact with any other particles or energy in the vicinity. The collective effect of billions of electrons moving in concert could be substantial. We are interested in whether this dynamic system can create a region where energy finds it difficult to escape. This is not a physical barrier in the traditional sense, it is a barrier created by fields and energy dynamics. Think of it like a vortex. Water spirals rapidly in a vortex. Objects caught near the edge can be pulled inwards. It becomes difficult to escape the swirling flow. Could our spiraling electron shell create a similar effect for certain forms of energy? When electrons spiral at high speeds, they lose energy. This is a known phenomenon called synchrotron radiation. Accelerated charged particles emit electromagnetic waves. This energy loss is a fundamental aspect of their dynamics. In our proposed system, this energy loss needs careful consideration. Could it be channeled or transformed? Could the interaction of the spiraling electrons with their own radiation field lead to unexpected emergent behaviors? These are questions we must explore. The system is complex and highly nonlinear. One fascinating concept in general relativity is frame dragging. A rotating massive object like a black hole twists spacetime around it. This is the lens-Thirring effect. Objects nearby are dragged along by this spacetime current. Could our spinning electron shell exhibit an analogous effect? The rapidly rotating electromagnetic fields and the moving charges might create a kind of drag on other fields or particles. This would not be true spacetime curvature, but it could be a similar effective force, an emergent property of the system. Stephen Hawking made a startling prediction. Black holes are not entirely black. They should emit a faint glow of radiation. This is known as Hawking radiation. It arises from quantum effects near the event horizon. Pairs of virtual particles are constantly popping in and out of existence. Near a black hole, one particle might fall in, the other escapes, carrying energy away. This causes the black hole to slowly evaporate. It is a profound connection between gravity, quantum mechanics, and thermodynamics. Could our spinning electron system produce an analog of Hawking radiation? This is a tantalizing possibility. If the electron shell creates an effective boundary, a kind of horizon for certain excitations, then quantum fluctuations near this boundary might lead to particle creation. These would not be the same particles as those from a black hole. They would likely be photons or other electromagnetic excitations. The mechanism would also be different. It would involve quantum electrodynamics, not quantum gravity directly. The similarities would lie in the mathematical description. The process might involve the conversion of vacuum energy into real particles. How could we actually test these ideas in a laboratory? Several existing technologies offer promising avenues. Tokamaks, designed for fusion research, already create dense rotating plasmas. With modifications, they might be adapted to generate the required electron shell configurations. The strong magnetic fields and diagnostic tools in tokamaks are well suited for such experiments. We could probe the electron shell with laser beams or particle beams. We could look for changes in their trajectory or energy. High-intensity lasers are another powerful tool. Lasers can create dense plasmas. They can accelerate electrons to relativistic speeds. Carefully shaped laser pulses might be used to form and spin the electron shell. Ultra-short laser pulses could then act as probes. They could measure the properties of the fields and particles within and around the shell. Detecting subtle shifts in light frequency or polarization could reveal the presence of gravity-like effects. The precision of laser-based measurements is a significant advantage here. The path to creating such an artificial gravity analog is not smooth. There are significant physical limitations to consider. Electrostatic repulsion is a major one. Electrons all have negative charges. They naturally repel each other. Packing them densely into a shell requires overcoming this immense repulsion. The confining electromagnetic fields would need to be extraordinarily strong. This presents a substantial engineering challenge. Generating and controlling such fields is at the cutting edge of current technology. Another hurdle is maintaining the stability of the electron shell. A dense collection of rapidly moving charges can be prone to instabilities. Plasma instabilities are well known in fusion research. Similar issues could plague an electron shell. The shell might break apart or develop unwanted oscillations. Sophisticated feedback systems might be needed to keep it stable. This requires a deep understanding of plasma physics and control theory. These are not trivial problems to solve. At very high densities and energies, other quantum effects come into play. Electron degeneracy pressure, which supports white dwarfs, would also be present. This pressure resists further compression. If the fields are strong enough, we might even approach conditions where pair production occurs. The concept of using spinning electron shells as a gravitational analog is ambitious. It pushes the boundaries of current experimental capabilities, yet its potential payoff is significant. If successful, it could provide a laboratory testbed for aspects of quantum gravity. While not directly probing quantum gravity itself, it would allow us to study analogous quantum field phenomena in curved, effective spacetimes. This could offer valuable insights into how quantum fields behave in extreme conditions. This system could serve as a bridge. It connects the well-understood realm of electromagnetism with the more mysterious world of gravity. By creating analogs, we can test theoretical ideas that are otherwise inaccessible. For example, we could explore information loss paradoxes in a controlled setting. We could study the thermodynamics of these artificial horizons. The lessons learned might guide the development of a full theory of quantum gravity. It offers a different kind of window into the universe's deepest secrets. This proposal is an invitation for critique and collaboration. The scientific community plays a vital role in vetting new ideas. Scrutiny from experts in plasma physics, quantum optics, and general relativity is essential. Collaboration between theorists and experimentalists will be crucial. Different perspectives can help identify unforeseen problems. They can also uncover new possibilities. This is how science progresses.